In this video, we are going to talk about autonomous differential equations and population dynamics. First, we will define what an autonomous differential equation is. We'll look at two models of population dynamics. We'll look at exponential growth and logistic growth. Then we're going to step back and we're going to look at how to do qualitative sketches of the solution y of t. In particular, we're going to be sketching the solution of a differential equation without actually solving the differential equation. So this is kind of interesting. And then we'll continue with our look at population dynamics. Exponential growth says the rate of change of y is proportional to the current value of y, and the population will grow exponentially for all time. Logistic growth, the growth rate still depends on the population, but is replaced by a function so that at some point there's a saturation level or an environmental carrying capacity, which is the upper bound which the population can grow. We'll also look at the critical threshold model, which gives us a threshold below which growth does not occur. So in this model, if y will either, or the population will either approach zero, go to zero, or will grow without bound, depending on whether we initially start with a population less than or greater than t. So again, the idea is t is a threshold. If you don't meet that threshold, your population will die out. Once you meet the threshold, your population will grow without bound. And then last, we have the logistic growth with the threshold. And this is very similar to the threshold model, but now we cannot grow necessarily without bound. So if y starts below the threshold, then y declines to extinction. On the other hand, if y starts above the threshold, then y eventually approaches a saturation, also an environmental carrying capacity, K. And this last topic here is something I probably should have had with the graphing, but I didn't have room for it. So an asymptotically stable solution is one where values close to the equilibrium will be attracted. They get trapped by the equilibrium and cannot move away. An unstable equilibrium solution is one that even solutions that start very near the equilibrium will tend to move away. The only way to guarantee the solution will remain at an unstable equilibrium is to start exactly at the equilibrium. So an autonomous differential equation is an equation in which the independent variable does not appear explicitly. Here we have dy dt is equal to f of y. So we don't have any functions of t. So that's what we mean by the independent variable does not appear explicitly. We either have the derivative of y or we have y. We will discuss these equations in the context of growth or decline of species population. The equation dy dt equals f of y is separable, so the previous video session on separable equations is applicable, but the main purpose of this section is to show how geometric methods can be used to obtain important qualitative information. That's again, we're going to learn how to graph the function of the solution without actually solving the equation. So we're going to obtain qualitative information directly from the differential equation without solving the equation. Of importance are the concepts of stability and instability and solutions of differential equations. Our first model is of exponential growth, and the differential equation is dy dt is equal to r times y. So in other words, the rate of change is proportional by this factor r to the current population. So r is considered the growth rate or the growth decline. So if we solve this, and this is an easy linear equation to solve, if we solve this, we get y naught equals r, or y of 0 equals y naught, and y is equal to y naught e to the rt. Then for different initial values, we can sketch curves, our solution curve. And since we have an equation for the solution right here, it's very straightforward to graph. And you can see from these graphs that the population will continue to grow exponentially, and there's no bound to the population growth, which is really not realistic, because after a population gets to reach a certain amount or large number, then generally there's a scarcity of resources, which will tend to start slowing the growth rate. For that reason, we have the logistic growth model. Again, dy dt is going to be proportional to y. So the change in population is proportional to the current population, but instead of just a constant r, we have it y multiplied by a function h of y, which we set equal to r minus ay. And what this does, in effect, is when y is small, this becomes small. So we're essentially multiplying by r when y is small. And then as y gets large, however, it starts to become more noticeable. And when it's large enough, essentially our growth rate will become negative. And that is exactly summarized here. So the growth rate still depends on population, but r is replaced by a function h of y. Hy is approximately equal to r when y is small. Hy decreases as y grows larger, and hy becomes negative when y is sufficiently large. So for a large enough population, our population will start to decrease. So here we have our function. dy dt is equal to r minus ay times y. Again, this is our function h. So r minus ay times y. And we often rewrite this in this form. Dy dt equals r 1 minus y over k times y, where k is equal to r over a. And the reason why we do this is this k has a special meaning. It's called the saturation, or the environmental carrying capacity. And we will discuss that as we look at this model more. This differential equation is solvable, and we will solve this differential equation in a minute. But one, just to note, it's certainly not as straightforward as the previous example. And for that reason, and also for more complicated differential equations, we're going to look at some tools to give us a quick look at a qualitative sketch of the solution of this differential equation without actually solving the differential equation. And the tools we use are really similar to like back in first year calculus, we use derivatives and second derivatives to help us do a quick qualitative sketch of many functions. And so we're going to use many of those same ideas. We're going to look at critical points. We're going to look at the first derivative to see where the function is increasing or decreasing. And we're going to look at the second derivative to look at concavity. Our first step will be to graph y versus f of y, where f of y is dy dt. So again, we're not graphing y of t, but we're graphing y compared to we're graphing y and comparing it to its derivative. So when you look at the graph, you have to keep that in mind. You're not looking at y versus t. It's not a graph of y. It's a graph of y versus its derivative. So our function f of y is given by dy dt, and that's equal to r 1 minus y over k times y. So I have that written here. It's r 1 minus y over k times y. And this form where you have f of y equals essentially a y squared is a parabola. So I have the equation of the parabola. I put this equation into a parabola form, but just because I'm so used to looking at parabolas in terms of y's and x's, I called my f of y and my y x. So I could look at it and I solved, and I see the vertex is k over 2 rk over 4. I want to mention again, we are not graphing, this is not a graph of y, this is a graph of y and the derivative of y. So how derivative of y changes with y. So here, if I look at this parabola, and if I take a slope here to represent the rate of change or the derivative of the function, this is the rate of change of f of y. This is not the derivative of y. Now I have the general shape of my graph. I'm going to look at the equilibrium or constant solutions. So equilibrium, that's when nothing is changing. So that corresponds to no change or variation in the value of y as t increases. So what that tells us is if f of y, which is equal to dy dt, is equal to 0. And the zeros or f of y are called critical points. So we want to look for critical points. We'll set f of y equals to 0. So here is our f of y, r times 1 minus y over k times y equals 0. So since this is a polynomial, either this part to be equal to 0, either 1 minus y over k is equal to 0, or y is equal to 0, and solving this equation will give us y equals k, or we have y equals 0. Those are our two zeros where f of y equals 0. So this is also part of our parabola. I can label those points now. Our critical points are 0, 0, and k, 0. That means our equilibrium solutions, also again, equilibrium solutions is when dy dt is equal to 0, when things are not changing. Our first equilibrium solution is phi1 of t is equal to 0. Our second equilibrium solution is phi2 of t is equal to k. One other comment, we are solving this here, these equilibrium points in the parabola with the vertex for the general logistic growth equation. So if you want, you can just remember this is where the vertex of the parabola is, and then I would just calculate the critical points because that's easy enough. And then you can always just draw the parabola from there. And actually, I'm also going to remind you that the parabola, it actually does go negative. It continues beyond. So far we've drawn the graph of y versus the derivative of y, and we've drawn our equilibrium and constant solutions. Our next step is to consider dy dt to determine where y is increasing and where y is decreasing. Looking at this graph, I'm going to warn you, so this is wrong. This is not a graph of y, so this is not where y is increasing and then y starts to decrease. This is a graph of the derivative of y. This is where the derivative is increasing, in other words, where it's accelerating. This is where it's decelerating. But what you can see from this graph is this whole parabola arc here between 0 and k, the derivative of y is positive. So I have this note here, dy dt is positive for y between 0 and k. Again, this is a graph of the derivative of y. So here, the derivative of y is positive, meaning y is an increasing function of t for y between 0 and k. And the way we indicate this on this graph, because somehow we have to capture that information on here, is with these red arrows saying that it's increasing in this region here. Then we can look at this portion of the graph where k is greater than 0, and you can see that f of y is negative. In other words, the function y is decreasing. And we indicate that by saying over here on this portion of the axis of y, that with the leftward arrow. So here I noted that. And then also, I noted this here, we're going to draw arrows for a phase line. Rightward arrows indicate an increasing function and leftward arrows indicate a decreasing function. And again, we have these arrows because we want to talk about y, so we're doing it along the y-axis, but we don't really have a graph of y here, so we have to do it with these arrows. And this y-axis now is what we call a phase line, and customarily we represent it vertically. And here is my phase line with y, and notice I changed, so I moved my little y versus f of y graph here for reference, and now I'm changing my graph, so now I'm going to start graphing y versus, or t versus y, y depending on t. Here's my phase diagram, my y-axis, which corresponds to this y-axis. I have k, the value of k, so between 0 and k, my y function is increasing, so I denote that with the blue arrow. And then when y is greater than k, right, we have y is decreasing, so I now indicate it with a blue arrow going down. I don't know why in this one it's red and this one's blue, but that's the way it is. And then I also did put my my critical points, my 0 and my k, I have them marked in red on my phase line. And again, my phase line is just an echo of my y-axis. And I'm just going to make that note again, dy dt, I'm using the red arrows on my dy dt graph to show where y is increasing and where it's decreasing. I also have that in my phase line. My next step is to consider the second derivative d2y dt to determine concavity. And I have this written out here. So d2y dt squared is just the derivative, and then you take the derivative again with respect to t. So it's just d dt, dy dt. But dy dt is just equal to f of y. Now I have the derivative of f of y. So remember, y is a function of t, so the derivative with respect to t of f of y is fy of f prime of y times dy dt. Again, by the chain rule, after I take the derivative f prime of y, I have to take dy dt. And so now what I have is this is equal to f prime of y, and then again, this is just f of y. So d2y d dt squared is equal to f prime of y, f of y. And this is where we get the graph is concave up. The derivative is positive when y double prime is positive, and that's when f and f prime have the same sign. It's concave down, or the second derivative is negative, when f and f prime have different signs. So I also have that summarized over here in the fourth bullet. We're looking at the second derivative. The graph is concave up when f and f prime have the same sign, concave down when f and f prime have different signs, and I kind of just did that derivation over here with my multiplications with the little asterisk. And actually I should move this so you can see my lovely derivation. Now I'm going to use this graph to look at the second derivative. So in the interval between 0 and k over 2 over here, you can see that f is positive, and you can see the derivative is also positive, right? This, if you draw a tangent line over here, it's increasing. So they both have the same sign, which means in this interval, our graph is going to be concave up. Between k over 2 and k, that's this interval here. Again, f is still positive, right? It's not, hasn't gone down here to the negative, but you can see that it's the derivative is negative, right? If you draw a tangent line, it would be negative. So in this case, they have different signs. So in this portion of the graph of y versus t, we're going to have a curve that's concave down. And then for k, for y greater than k, here we have f is negative. It's crossed over to negative territory, and the derivative is still negative. So they have the same sign, so we switch back to concave up. So you can also see there's an inflection point at k over 2 and at k, because that's when concavity changes. And I wrote down my inflection points here. And now I'm ready to draw my graph. I start by putting in my equilibrium solutions. I should probably add that here. The two things we're going to use now to do the graph are first the derivative, where the function's increasing, and we're going to use this phase diagram here. So between 0 and y, our functions are going to increase, and they're going to approach this value k. Remember I had mentioned that k was special. I mean, we totally rewrote our equation to include this k, and the k is our maximum, our carrying capacity or saturation level. We'll talk about that a little more. But essentially between 0 and k, we're increasing. And then we had also found before, and we notated it with this blue arrow, for y greater than k, y will be decreasing. So we're going to have decreasing functions here. The second thing we're going to look at is concavity. Remember, we have two inflection points, k over 2 and k. So between 0 and k over 2, again, we have an increasing function, and we're concave up. So we're concave up, we're increasing. The moment we hit k over 2, though, we're still increasing, but we're going to go and turn concave down. Similarly, here's another solution with a different initial value, right? This was where the first initial value is, whatever y is here. This is our next solution with initial value, whatever y is here. We're increasing, y is increasing, and then the moment we hit k over 2, we're still increasing, but we're going to be concave down. Looking at the interval between k over 2 and k, now we're going to be concave down. We're still increasing, right? By our arrows, we're still increasing in this interval. So we're increasing, and we're going to be concave down. Another initial value here gives us another solution, and we're concave down. And finally, when y is greater than k, our functions are decreasing, y is greater than k, and we're concave up. A note, the curve may seem to intersect the equilibrium solution, y equals k, but if I drew it that way intersecting, that was unintentional because they do not intersect. by the uniqueness theorem that we had in some previous video. Uniqueness states only one solution can pass through any given point in the ty plane. And all the solutions are asymptotic as t approaches infinity, but they do not intersect in finite time. Finally, I told you everything was going to approach this particular equilibrium solution. That's because this equilibrium solution is equal to k. And k is the upper bound that is approached but not exceeded by growth populations starting below this value. We refer to k as the saturation level. Remember, I had talked about that we rewrite our equation dy dt in terms of a k value, and we introduce this k value, and it is significant because that's kind of the limit of where a population can go. If you start less than k, you cannot exceed k. It's the saturation level. It's the idea that at some point you can't grow exponentially forever. Comparing exponential growth to logistic growth, exponential growth is a linear differential equation, and you can see we can have growth without bounds. The moment we have this nonlinear equation, no matter how small this y over k is, so even if it looks a lot like r times 1 times y, if this is very small, even for a small number, what these graphs tell us is that our growth is limited by k. So in other words, no matter how small the nonlinear term, in other words, no matter how small this y over k multiplied by y is, solutions of this equation, of the nonlinear equation, approach a finite value as t approaches infinity, as opposed to the linear equation, which grows without bounds. So even a tiny nonlinear term has a decisive effect on the solutions for larger values of t. And one final note to point out, remember, we haven't even solved this differential equation yet, and we have quite a bit of information about what the solutions look like. That said, this equation is separable, so we can gather all our y terms onto one side equals r. I have this little algebra thing here so that this will become easier to integrate. So I integrate both sides with respect to t. I get this equation here, and we have an initial value, and eventually we come down till we get this equation that y equals 1 over y is equal to 1 minus y over k c e to the rt. Solving for the initial value, we get y equals y naught k over y naught plus k minus y naught e to the minus rt. So this is the general solution for the logistic growth differential equation. And if you graph different solutions or just kind of analyze this analytically, you'll see that the graphs will kind of match the shape of our qualitative sketch. I should also note, when I saw the initial value, I assumed y naught was between 0 and k so that I could remove the absolute value from my logarithms. But for y greater than k, you can use a similar procedure. Now we are ready to talk about asymptotically stable solutions and unstable equilibrium solutions. So for each y naught greater than 0, and here I've illustrated 1, 2, 3, 4, 5, 6 different y naughts and 6 different initial conditions. The solution approaches the equilibrium solution asymptotically as t approaches infinity. So here they all approach k. That is, after a long time, the population is close to the saturation level k, regardless of the initial population size, as long as it is positive. So it approaches an asymptote. An unstable equilibrium solution, on the other hand, even solutions that start very near 0 grow as t increases and approach k as t approaches infinity. The only way to guarantee the solution remains near 0 is to make sure its initial value is exactly at the equilibrium. So here in this equation, and in this differential equation, the equilibrium solutions were y naught equals 0 and y naught equals k. Those are the steady states. So that we can classify these equilibrium solutions, I want to remind you what it is to be an asymptotically stable solution, which means once values get close to this equilibrium, this asymptotically stable equilibrium, they will be attracted and then end up staying at the equilibrium solution. In other words, they get trapped by the equilibrium solution and cannot move away, sort of like a black hole. On the other hand, an unstable equilibrium solution means that even solutions that start very near the equilibrium will tend to move away, and the only way to guarantee the solution will remain at an unstable equilibrium is to start exactly at the equilibrium. And the reason why it's called an unstable equilibrium is while equilibrium points are extremely stable, in fact, nothing ever changes at them, if you look, they're kind of fragile, because if you look just a little distance away from your equilibrium point, then your solutions can go and they could grow unbounded. They go wherever they want. So in our example, for each starting value, y naught, each initial value, all of our solutions are attracted to our equilibrium solution, phi of 2 equals k. So phi of 2 equals k is an asymptotically stable solution. On the other hand, if we look at phi of 0, even if we were incredibly close, our initial condition were very close to 0, we would end up approaching k anyway. So phi 1 of t equals 0 is an unstable equilibrium, and the only way to guarantee the solution remains near 0 is if the initial value is exactly 0. Now that we've talked about the exponential growth and logistic growth, as well as how to do a qualitative sketch of the solution of a differential equation without actually solving the differential equation, we will do an example of logistic growth. The logistic model has been applied to the natural growth of a halibut population in certain areas of the Pacific Ocean. Let y measure in kilograms the biomass of the halibut population at time t. The parameters in the logistic equation are estimated to have values of r equals 0.71 per year, and k is equal to 80.5 times 10 to the 6 kilograms. If the initial biomass is y naught equals 0.25 k, find the biomass 2 years later. Also find the time tn, for which y of tn is equal to 0.75 k. Here we have the solution for the logistic equation, since it's a logistic model, and we also have the solution for the initial value, y0 is equal to y naught. So plugging in for y naught is equal to 0.25 k, and then we also have k here. I guess that's it. Y naught, we plug in for y naught, k minus y naught here, e to the minus 0.71 t, since we're given r as well. After some algebra, we reduce our equation y is equal to 0.25 k over 0.25 plus 0.75 e to the minus 0.71 t. So if we want to find the biomass 2 years later, we can plug in t equals 2, and we get something approximately 47.173 times 10 to the 6th. To find Tn such that y of Tn is equal to 0.75 k, we start with the initial value equation, and then we do some algebraic manipulation, starting with multiplying both sides of the equation by the denominator. And we continue to do some more algebraic manipulation until we get to this equation here, which is e to the minus rt equals y naught times k minus y divided by y over k minus y naught. Here we take the logarithm of both sides, do some more algebra, till eventually we get t sub n is equal to minus 1 over 0.71, plugging in for r, natural log of 0.25k, that's plugging in for y naught, times k minus 0.75k, all over 0.75k times k minus 0.025k. After you calculate this, you get approximately 3.095 years. And here are some solution curves. And this is where we will stop this video. We will do another part 2 to finish this topic. So in this video, we talked about autonomous differential equations and population dynamics. We started with the definition of an autonomous differential equation, which has the form dy dt is equal to f of y. Our first example was exponential growth, where dy dt is equal to r times y. And this model basically said that the rate of change of y is proportional to the current value of y. And in this model, it predicts population will grow exponentially for all time. However, it is clear such ideal conditions cannot continue indefinitely because eventually there'll be a limitation on resources, which will reduce growth rate and bring an end to uninhibited exponential growth. So we looked then at logistic growth, which was very similar to exponential growth in that dy dt is dependent on y, but now instead of a constant r, it's dependent on a function h of y. And we chose h of y is equal to r minus ay. And with this choice, we see that when y is small, when the population starts out small, this h of y essentially looks like r. As y gets larger, then h of y gets smaller, and as y gets very large, h of y becomes negative. So as y becomes very large, our growth rate will start declining. The last topic we did was qualitative sketches of a solution y of t. So given a differential equation, we would sketch the solution of the differential equation without actually solving the differential equation. And the steps we took for that is first we graphed y versus f of y. And remember, f of y was dy dt. So we graphed y versus dy dt. Then we looked at equilibrium or constant solutions, which corresponds to where there's no change or variation in the value of y as t increases. So in other words, f of y, which is equal to dy dt, equals 0. These zeros of f of y are also called critical points. Then we looked at the derivative dy dt to determine where y is increasing and where y is decreasing. And we drew arrows on the phase line to indicate where y is increasing and decreasing, because remember, the graph we have here is not of y versus t or of t versus y, it is of y versus f of y. The next point we considered was the second derivative d2y dt squared to determine concavity, and we found that the graph is concave up when f and f prime have the same sign, and it's concave down when f and f prime have different signs, and that is because of this equation here. d2y over dt squared is equal to d dt of dy dt. In other words, you take dy with respect to t and then take the derivative one more time to get the second derivative. Well, this here is equal to d dt times f of y because f of y is equal to dy dt. Now, if you have the derivative with respect to t of f of y, that's f prime of y, and then using the chain rule times dy dt. So this here is equal to f prime of y, and again dy dt is equal to f of y. So here, if we want to know the second derivative, it will have a positive sign when f prime of y and fy have the same sign. d2y dt squared is negative or concave down when they have opposite signs. And then last, we drew the phase line on a new graph, and then we drew y versus dy dt using the information we had gathered in previous steps. In this section, we did go over exponential growth and logistic growth. We will continue in our next video to talk about the critical threshold model as well as the logistic growth with the threshold model. And we also talked in this video about asymptotically stable solutions and unstable equilibrium solutions. So that's it for this video. There will be a second part, as I said, to cover these last two topics. Thank you for watching.